My name is Christopher Mickeljohn, and I'm going to continue our lectures on programming weak synchronization models. So for this talk, I'm going to review conflict-free replicated data types. I'm going to look at one special case of a conflict-free replicated data type, the observe-remove set, and then I'm going to talk about problems of composition. So to review, what are CRDTs? CRDTs are abstract data types that can look like sets, counters, registers, flags, or maps. That satisfy the property of strong eventual consistency on a per object basis. What this means is that under concurrent additions with minimal coordination, I always have a way to take any two objects and deterministically merge them, allowing each replica to converge just by observing all of the messages in the system. And CRDTs are formalized using what's referred to as bounded join semilattices. Which mathematically means that for any two possible states the object can take on, there's always a way to join them and combine them, so merge them together. Now, one special case of a CRDT is what's referred to as the observe-remove set, which allows us to add and remove elements with minimal coordination and guarantee get the same outcome under concurrent additions. It's worth noting that this set under concurrent additions and removals, which normally don't commute in a sequential system, they will resolve to the concurrent addition winning. So in this example, I'm going to have three copies of the data here represented by replica A, B, and C. And I'm going to model the state of each replica as a triple, which will be the value in the set, a set of unique additions, and a set of unique removal tokens. And we can see that here. And so what this basically says is when I added the value 1 to the set, I generated a unique token here, alpha, represented by this A, and I put it into the add set. So 1, this set of A, the singleton set of A, and the empty set of remove says that 1 exists in the set because it was added at logical time A with no removals. Now concurrently here, if I add 1 to the set at replica C, before it's observed the addition from A, it will generate a different token, here represented by beta, which shows that it was added to the set at logical time beta and not removed. Now to model removes in a monotonic way, in a way that always merges, I take the additions and I union them with the removals. And so here it shows that I saw 1 added at logical time B, and then I also saw it removed at logical time B. And so at this point of the execution, the set has no values in it. And so these here are the replica-to-replica messages where the values are propagating between replicas. Now at the end of the execution, the way I achieve convergence is that as each replica receives messages from the other replicas, it just takes a pairwise union of the adds and the removes for every value in the set. And we see that here at the end of the execution, 1 is still in the set, because while it was added at time B and removed at time B, it was added at time A and nobody removed it at logical time A. So in this example, 1 remains in the set because the concurrent addition and the concurrent removal, the concurrent addition from node A, 1. So let's talk about problems of composition. So in terms of composition, we're going to consider observe-remove set. We're going to drastically simplify it here by only keeping 2 replicas in play. And I'm going to have it so 1 remains in the set. It's basically going to be the same situation as before. 1 will remain in the set. I'll have an addition or removal and a concurrent addition that will win. Now, if I wanted to program with the CRDT, for instance, if I wanted to take the value of the CRDT, the set with 1 in it, and apply a function to that set, such as doubling the elements in it to make this as simple, the way I could trivially build this is a process that reads the set as it changes each time, and then applies the update here. So we see that the set was 1, it went to 2, the set was empty, it went to nothing, and then it was 1, and it went to 2. Now, in a distributed system, to achieve fault tolerance, in the same way I replicate the data, I would replicate the entire computation. So I would have the computation running here and the computation running here. Now, if for some reason, and now as we've seen with CRDTs, if messages get delivered out of order, it doesn't change the result. They still will always achieve the correct convergence. However, if I, in this case, trivially take the values and I don't take this metadata and map it through the function, The problem I can run into is that a delayed message can change the outcome of the execution. It doesn't necessarily merge. I have no way of merging the outcomes of the computed value in the same way I have that I can operate on the source values because I don't have the metadata. And so while some parts of the computation, such as this section highlighted here in yellow, while some parts of the computation will converge correctly, any message that's delayed that doesn't carry that metadata will not compute the correct result. And so what we've seen is that while the observer moveset in isolation allows us to model additions and removals without coordination, as soon as we go to read that value and do anything with it, we break out of the safety because we no longer carry around this internal metadata, which is the important part of ensuring convergence. And so this is what we refer to as the composition problem. And this is what we'll be discussing in our next lecture.